Welcome. Today we're going to be discussing Chapter 4, Discovering the Secrets of the Nucleus. Our story starts at 5:30 a.m., July 16th, 1945. Our place is Alamogordo, New Mexico. In the desert, there's a small 6-kilogram pile of plutonium set up in a bomb on a tower in the desert. When that explodes, it releases a detonation with the power of 20,000 tons of TNT. Releases a temperature of 10,000 degrees, hotter than the sun. People looking at it from 20 miles away become temporarily blinded, and it releases a mushroom cloud that goes 8 miles into the sky. The 100-foot tower is vaporized, and the sand all around the tower have been glassed for a half mile. This is the power of the atom and splitting the atom. Yet, this has come a long way from just 50 years previously when we first discovered radiation and radioactivity. So, our story actually starts way back in 1896 with an Antoine Henry Becerra. He was studying at École Polytechnique Paris, and he was looking for a connection between X-rays and phosphorescence. It was believed that light would shine into these minerals that would glow, and this glow would create X-rays that could then be developed onto a photographic plate. The idea that when X-rays hit a photographic plate, it causes them to brighten where struck, or actually darken where struck on the negative. And that's the whole concept of X-rays to determine whether your bone is broken. We shoot a bunch of X-rays, where your bones are, they absorb the beams. Where your bones are not, absorb the X-rays that penetrate your skin and go behind it, though we see dark where it absorbed and light where it hasn't absorbed. So he was studying that with a uranium mineral that's like a potassium uranyl sulfate. It's a K2U2SO42, something like that. After Wilhelm Röntgen's discovery of X-rays just the year before. So, like all good science, someone finds something really cool, and all the others starting to say, "I got to get me some of that." And so he starts looking at, I'm going to try to look at X-rays. So what he's doing is he would shine light on this uranium ore and then put it up against a photographic plate that's covered in like brown paper. The idea that no light is going to shine through the brown paper onto the plate,
and then the plate darkens where it absorbs.
so he's like, "Oh, it seems to be working," because that where he put the uranium, it caused the expected result to happen. Well, they ran into a period of cloudy weather, and so he puts the uranium in the drawer right next to the photographic plate and leaves it in there for a couple days until the weather's nice again. Well, it just so happens he decided to, maybe this will make a good control. A control being an experiment you test that should have a negative result, and that's where you have something as a comparison. Well, he went in and developed that plate, and yet, despite no light being shined on that uranium, it still had that same effect. So he thought he found, was this from X-rays that did not need the light? Well, the answer is no. After much more time and much more study, he finally found a new type of radiation. Well, 2 years later, Marie Skłodowska-Curie was a student of Becquerel, who was beginning to study this. Now, like I think there's a pretty good show, a pretty good movie, like dramatization of Marie Curie's life out there on Amazon Prime. Of course, they probably took some liberties, but it's a pretty good way to try to get a better story. But was a Polish immigrant at a time when Poland was no longer a country. Poland was a like a province of Russia. Essentially, Russia controlled Poland, and so Poland didn't have its autonomy. So she had gone to try to get school, fought her way there, and she got schooling, and she's the one who coined radioactivity, the idea that the spontaneous emission of radiant energy and or high energy particles from the nucleus of an atom. She was the first one to recognize that it was from the nucleus. That this took a lot of convincing for a lot of people because they didn't believe, well, the nucleus up until now hadn't really been reactive. Everything else had been the electrons in the outer layer, the electrons in the outer layer. Why would the nucleus suddenly react? Well, that is the case. That is the case. She found other types of radioactive elements, not just this uranium ore. Her and her husband, Pierre, discovered radium and polonium. And in 1903, she became the first woman to win the Nobel Prize, which she shared with Pierre and Henri. And it wasn't and that was just for the discovery of radioactivity. And in 1911, which would 9 years later, she became the first person, period, to win a second Nobel Prize. The first one was in physics. This one is in chemistry for the discovery of her originally radium. If you think about radium, radiation, and polonium, which she, of course, named as good old Poland. Now, Pierre would have probably shared that with her, but unfortunately, he was struck dead by a carriage several years before. So that's rough. She becomes one of the key figures in history. Whenever we point to, look at women's rights, she is one of the key people we point to. She got an element named after her, curium. She got a radioactive unit named after her, the Curie. So she was quite something in the science world. And in fact, it ran in the family. In 1935, her daughter, Irene Joliot Curie, and her husband, Frédéric, won the Nobel Prize for radioactive isotopes of nickel, phosphorus, and silicon. But this all came from Henry's willingness to test that control, to test that plate. He would have been spending many a long day studying, going in the wrong direction, if not for that little piece of serendipity. And sometimes serendipity goes a long way in science. You get lucky, you test something that you didn't really think about, and then next thing you know, wow, that it kind of goes, and your research goes in a completely different direction because you're willing to test the whole thing and not just a little bit. You try something that you don't think is going to happen, and not you try something that's don't think is very important, and it suddenly makes the world a difference. Well, in 1899, Ernest Rutherford was continuing this research, and he found that there's at least two types of radiation, not just the one that discovered by Marie. He discovered that there's alpha and beta. Now, there was also gamma radiation discovered by P.V. Villiard later, but alpha and gamma. The alpha radiation, as we can see, it's big, it's bulky, it doesn't have very much penetrating power. It can be stopped by paper, metal, foil, thin clothing. So it's not going to penetrate the skin. Beta radiation has a little bit more penetrating power. It has metal sheeting. It could be blocked by metal sheeting, dense wood, and heavy clothing. But so it can penetrate a little bit in the body. And as we'll see in gamma radiation, there's very good penetrating power. It needs thick walls of lead, thick concrete, or even like large bodies of water to block gamma radiation. Well, he would eventually get the Nobel Prize in 1908 for his discovery of alpha and beta radiation, the two different types. But he found that it carried radiation from the nucleus, and this can actually change the atomic number and the mass number, or neither, depending on what type of radiation we have. And we saw that he could also undergo a radioactive decay chain to become stable by transforming between elements. Now, one thing to note is we need to go back to our nuclear notation that we looked at in the previous thing, where we have to include the mass number and the atomic number. Sometimes we can leave off the atomic number because that's understood to be the element itself, but we almost always need to include the mass number to say what isotope we have. So carbon 14, so you could say C14-6, well, it's 14-6C, or you can just say carbon-14. But all these are because we need to emphasize radioisotopes, the isotope of an element that emits radioactivity. Carbon-14 is radioactive, carbon-12 is not. So that'd be carbon-14 is an example of a radioisotope. So let's actually define what is alpha particle. What is alpha particle and alpha radiations? Alpha particle is a high energy helium nuclei that is emitted by radioactive nuclei, and it travels at 5 to 7% the speed of light. So it's often represented by just alpha or 4-2 alpha, because helium is 2 protons, 2 neutrons. So mass number 4, atomic number 2, or it can be written as 4-2 helium 2 plus, because it's no electrons, it's just 2 protons, 2 neutrons together. Well, beta radiation is high energy electrons that are emitted by radioactive nuclei, and they move at up to 90% the speed of light, often given as beta, beta minus, 0, 1 minus beta, or 0, 1 minus electron. How this actually works, how do you release an electron from the nucleus, is the idea is that whenever you have a positive, you also have a negative. So what happens is a neutron actually shatters apart and turns into a proton and an electron and these beta particles. When it kicks out a beta particle, the neutron is converted into a proton. Kind of weird, kind of neat. Now, gamma rays are often the most forgotten of the types of rays, that they form of high energy electromagnetic radiation. They essentially have no mass and carry no electrical charge. Harder to block, harder to redirect, because they don't have a charge. They just go boom in one direction. They're often written as gamma or gamma or 00 gamma. The idea is that they have no mass and they won't really contribute. But of course, they have 100 times more penetrating power than beta radiation. So they can go a lot further and do more damage, and that it's harder to stop. All this can lead to things such as ionizing radiation. Ionizing radiation is any form of radiation that's capable of converting electrically neutral matter into ions. So they strike the matter and turn it into a proton by stripping off an electron. Some of this, and that's where it comes in and does damage to, like, say, DNA. It can ionize your DNA molecule, and this cause it to denature and all the sort of things, so it doesn't work like it should. But gamma radiation can be good. It's used to detect flaws in metal parts and structures. You essentially put a photographic plate up to the metal part, you shoot it with the gamma radiation, any cracks will let the gamma rays through, and so you can see them, those tiny little cracks that maybe can't be seen with the naked eye on the photographic plate. Say, oh, there's a little weakness here in the center of this that we couldn't really see, but the gamma rays can penetrate through that little weakness. So now back to our decay chain. So things like uranium undergo multiple different decays. Where the uranium 238 goes to alpha decay, then it goes two more beta decays down to so uranium 234, then it undergoes alpha decay, alpha decay, alpha decay, alpha decay, alpha decay, and then it can go beta beta or beta alpha or all sort of things. It's eventually going to go to lead 206. Within those chains, that's where you're going to find things like radium, radon, and polonium. Some of those elements that were originally discovered by Marie Curie by looking at pitch blende. Pitch blende, of course, is metal, uranite ore that contains UO2s and UO3s. It's black like pitch. And found that uranium 238 is found in 99% abundance. That uranium was originally discovered in 1789 by Martin Heinrich Klaproth, and it contains lots and lots of decay byproducts in there. So when Marie and Pierre Curie had to discover radium, they had to take lots and lots and lots of pitch blende and try to separate these different components and try to purify them out. So we can see a lot of nuclear math going on in here. Some of these, here's what the actual decay chains start to look like. We have things like tritium over here will undergo a beta decay to form a stable helium nuclei. This is not the most common isotope of helium, but it is a stable isotope of helium. So if you look at here, the mass number is 3. The total sum of all the masses here are 3, because 3 plus 0 is 3. The atomic number is 1, and the total atomic number is 2 plus -1, which is equal to 1. So all protons and all neutrons are accounted for. Carbon-14 undergoes a beta decay to form nitrogen-7. So remember, one of the neutrons gets turned into a proton, and so the shifts up 1 atomic number while keeping the same mass number. The first decay of uranium, of course, is uranium-238, 92, undergoes alpha decay and gamma decay to form thorium-234, 90. So 238 equals 234 plus 4. 234 plus 4 is 238. 92 equals 90 plus 2. So the element 90 is thorium, and look at the alpha product, the alpha decay. Oftentimes they leave off the gamma because the gamma doesn't really contribute anything. But so uranium-238, which is in 99% abundance of all uranium, will naturally decay over many, many steps, like 13 steps to lead-206. Uranium-235, which is a small component, will undergo multiple different decay steps to get lead-207. And things like curium will undergo something like 15 or so decay steps to go from curium-245 to bismuth-209. They all undergo many, many decay steps in order to get to a stable isotope, which point they can stop. Let's take a minute to try to calculate some of these. Let's actually practice some of these calculations. Make sure we fully understand this. Okay, so let's look at some of this nuclear calculations. If we have polonium-210, 84, and it undergoes an alpha decay. So alpha decay for 2. What would the other byproduct of this be? So you got to remember the total number of mass on both sides must add up. So if this is 84 down here, 2 plus 82 equals 84. If this is 210, then 4 plus 206. So 206 plus 4 is 210. So the element for 82 happens to be, I look on the periodic table, lead. If iodine 131 were to decay and form xenon 131, what would be the decay byproduct? So you got to think of it. The mass number 131 and 131, so whatever's decaying must not have a mass. Then it goes from 53 to 54. So this must be going up by 1. So 54 minus 1 equals 53. So this must be a beta decay because beta is our number. Hopefully that's a little bit clearer now. Sorry. Thorium-230-90 undergoes a decay to form radon-236-88. What must its decay product be? So 230, sorry, my bad. 226. 226 plus what is equal to 230? So 226 plus 227, 228, 229, 230, 4. 88 to 90, that's 2. So releasing an alpha particle. One more. What would undergo beta decay to form plutonium 239? Well, beta is 0 minus 1. So it must be 239, 93. 93. 239, 93, which is, I think, neptunium. Yes. So that is an example of simple atomic math. Now, in doing this, we finally found that magical field of alchemy, the idea that we can turn lead into gold. We've seen the first time an element is converted into another element. In 1919, the first artificial transmutation was done by Rutherford, where he used radium as an alpha emitter. And when he shot radium into nitrogen 14, the alpha particle fragmented off and produced a hydrogen atom and an oxygen 17 atom. Not the most common isotope of oxygen, but it is a stable isotope. This is the first case of real transmutation. Transmutation being, of course, the process of converting one element into another element. That was the whole major thing about alchemy. You hear about alchemists, they always wanted to turn lead into gold. They wanted to turn a base metal that was not super, well, super abundant, not super worth a lot, not super expensive, into something that could then make them rich. Of course, they also wanted the elixir of life, but main thing was turn lead into gold. Well, nowadays we can form something into gold, but unfortunately it's not lead, it is platinum. We can bombard platinum 198 with a neutron, thus forming platinum 199, which would naturally decay into gold 199 through a beta decay process. That's not the most common isotope of gold, that being gold 197. And the fact of the matter is, the cost of this, though, because you have to get not just platinum, which is already an expensive metal, but high purity platinum, the cost of doing this is actually far more than the amount of the cost of the gold you could get from this. So not really a worthwhile endeavor. The alchemist's dream still remains out of our reach. From this, we can actually kind of see how strange the nucleus truly is, because we've learned about alpha, we've learned about beta, we've learned about gamma, but there's actually more things that go on. I mean, if you look at it, there's a new type of decay that happens, which is the positrons. A positron is a subatomic particle that carries a positive charge but is otherwise identical to an electron, essentially a positive electron, which is hard to believe, seen as beta positive, 0, 1 plus, or 0, 1 plus E. This is from, like, if you got to think about it, the nucleus is a whole bunch of protons packed close together. Only when you think about positive charge in one place, they all repel each other. But that's not the case due to the intermix of protons and neutrons together. That there's some nuclear force that holds this together and keeps them from shattering off in all different directions. But occasionally, you can get a positron emission. And a positron, when it hits an electron, actually will neutralize each other out, like matter and matter and antimatter, and it forms gamma particles as both are eliminated. Now, there's also quarks, which was first proposed in 1964, but we wasn't being able to demonstrate until closer to 1967 by Jerome I. Friedman and Henry Kendall at MIT, and eventually by Richard I. Taylor at Stanford Linear Accelerator Center. But a quark is simply a fundamental particle that is composed of larger subatomic particles, such as protons and neutrons. That they come together. You have like something like 3 quarks to a proton, and 3 other types of quarks to a neutron. And essentially, we're swapping quarks when we exchange a proton to a neutron. They have like weird classifications like color, flavor, charm, and beauty that don't ask me. It's beyond me, and it's beyond the scope of our science. But the fact that then they have weird names like gluons, which is the subatomic particles that hold the quarks in the clusters, like glue. This is heavy duty physics that we won't really worry about. But just the fact that our fundamental particles, protons, neutrons, and electrons, we can still go smaller. But it's not quite what we're going to focus on. Now, when we think about stable nuclei, most nuclei, at least the early ones, have something like a 1-to-1 proton to neutron ratio, except for really hydrogen. But even then, deuterium is 1-to-1. When you look at helium, it's 2-to-2, and lithium it's something like 3-to-3, and beryllium 4-to-4, carbon 6-to-6. And when it gets into the heavier elements, it comes closer to 1 to 1.5 of protons to neutrons, especially in elements like lead and mercury. Outside this magical ratio, and these guys will naturally want to decay. So Rutherford eventually proposed neutrons in the early 1920s to help understand this magical ratio and what's going on. But a neutron wasn't fully discovered until 1932 by one of his students, James Chadwick. That the neutron, they understood the atomic number and the mass, but they found trouble trying to figure out where this missing mass was. So that's when Rutherford proposed there must be a neutral atom in there, the neutron. That some people had done some work and saw some mysterious particle being given off that didn't have a charge, and it wasn't until Chadwick did this experiment where he bombarded deuterium with gamma particles that he was able to see a neutron released and get an accurate measurement. That when he bombarded with gamma radiation, we ejected 1 neutron from the hydrogen core, and is able to measure that and get a good weight on it. Well, now that we've been able to see neutrons not really see neutrons, but like capture neutrons and eject neutrons with some regularity, in 1938, Otto Hahn, a German radiochemist, would go on to split uranium by bombarding it with neutrons. So what he found is that when he hit uranium-235 with a neutron, he got barium and another component. But see, the big thing here, why this is actually important, is that barium is something like 1/3 to 2/3 of the weight of uranium. That's 2/3 the weight of uranium. All the other decay fragments we've seen up until now have been small fragments. An alpha particle, which is a mass of 2, a beta particle, which has no mass and just atomic number change. Gamma, which was no mass and no charge. So when we saw barium after bombarding with the neutron, we saw on the first really big fragment. Of course, you didn't find krypton because krypton was a gas. But what he saw is that he had the first situation of nuclear fission. This is a loss that's much, much greater than just that of alpha, beta, or gamma radiation. He would share his results with Liza Meitner, who eventually would coin the phrase nuclear fission, that the splitting of the atomic nucleus into two or more larger fragments. Now, fission releases far more energy, and if this fission can be sustained, it can be very explosive. Now, U-235 is far more fissile, but yet it has a 1% abundance of all the uranium. So we kind of have a problem. It's very rare compared to uranium 238, but it's far more reactive, more efficient. You hit it with one neutron, it fragments into, say, tellurium and zirconium and 2 neutrons. Or if I hit it, it could fragment into barium, krypton, and 3 neutrons. And a lot of energy as it does this in both these cases. Now, we could have 200 different isotopes, all each representing a total of 35 different atoms. So we have a lot of different fragmentation possibilities. These are just the two that are probably best well known. This is the first example of a chain reaction. Chain reaction is a continuous series of nuclear fissions that occur when a neutron is released in the fission of one atom, which causes the fission of additional atoms, which in turn releases still more neutrons and produces still more fissions, and so on. So the idea here, one neutron hits it, we produce 3 new neutrons that hit 3 other atoms, and they each produce, say, 2 to 3 neutrons, and it keeps going in a chain reaction, and it builds more and more and more, producing more and more heat. Now, there is a minimum amount you need, because some of those neutrons will be lost. Some of the neutrons either won't hit hard enough, or they'll hit too hard, or they'll fly off and hit the wall of the container instead of hitting a reactive material. So some of it will be lost. So you need a critical mass, which is simply the minimum mass of fissionable material needed to sustain a chain reaction. Now, plutonium-239 can also cause a chain, and it actually is more efficient than uranium-235, and it has about 20% more energy when it does that. Now, here's where we get into the story. We've almost got up to our original starting point. The U.S. Army Corps of Engineers would either going to generate the Manhattan Project under the request of Albert Einstein. He wrote to the president saying, like, oh, this is some of the capabilities we have. We should try to do this before Germany gets the bomb. And so the Manhattan Project, we did production facilities in Oak Ridge, Tennessee, and Hartford, Washington, to produce different types of fissile material, and then put together in Los Alamos, New Mexico, to build the bomb. We had to do a lot of different work, and this was a big wartime effort to get this to go. And Oak Ridge, they would go on to, their job was to separate uranium-235 from uranium-238. Now, I think nowadays we have like just really, really, really powerful centrifuges. But back then, the way they used fusion. So what they did is they took uranium and converted it into a gas with UF6, that uranium hexafluoride. And then they allowed a process called effusion to separate the isotopes. This essentially, a fusion works is like, so you have a small porous material, and gases, when they strike the pores just right, they'll seep through to the other side. But the fact of the matter is, the lighter the material is, the faster they'll strike the pores, the better they'll separate. Now, this is only 3 AMU difference, so it's only a 4%, it's not even 4%, a 0.4% faster. But over time, in many separations, they could eventually separate U235 from U238. Well, essentially, their job was to turn 20,000 pounds of uranium ore to 112 grams of fissile
Material requiring
lot lot of separation for that to work. Plutonium 239 was manufactured at their Hansford plant. The idea being they have multiple redundancies, that if Oak Ridge failed to produce one type of fissile material, hopefully Hansford was able to produce it, so there'd be no one necessarily holding up one aspect of this. That what they do is they take uranium 238 and bombard it with a neutron to form uranium 239. And this could then undergo a beta decay. Apparently they used a certain type, a beta decay to form neptunium. And then that neptunium would then undergo another beta decay to form plutonium 239. The first decay takes about maybe a couple hours, a half-life of a couple hours. We'll talk more about that later. And then the decay to plutonium takes a couple days. But so they could generate that within a small period of time, but they had to bombard it. So now they needed to make the bomb. And so they had all these engineers and physicists going around putting them in. They had to safely store this and safely combine this in a way to do this. So the one way they actually store this is they store this in two subcritical masses. They have two masses that if something were to go wrong, and we get neutrons, they're not going to explode in the plane. So the uranium one is a pellet type bullet one, the little boy. That what happens is you have a ring on one side and you have a core on the other, and then when the bomb goes off, explosion flings these two masses together, and the ring fits around the core, and suddenly you have a critical mass, a supercritical mass, and with a initiator that would then give off neutrons like beryllium and polonium, neutrons off, and you only need two neutrons to begin detonation. The uranium bomb was a sure thing. Now the plutonium was a little bit trickier. They had a hollow shell, and so what you would have is, as what the Fat Man was implosion based, that you need perfect symmetry, that when the explosion crumples this down into a small pellet of supercritical mass where it would go off. Now, the original test that we talked about is in Alamogordo was the plutonium base. So we had at least two fat mans. The first one we detonated in the desert to make sure it worked, because that was the one we were not quite sure about. But the problem with all of this really is part of the cavalier attitude of the scientists at that time, and the lack of knowledge, military intelligence at its finest. That the chemists that were purifying the uranium didn't quite know all the hazards and safety protocols to store the uranium. In fact, our friend Richard Feynman down here went to the Oak Ridge facility. He was mainly working at Los Alamos. We went to the Oak Ridge facility to oversee some of the stuff and found some key problems there. Like they were storing the uranium too close to each other, thus accidentally creating some of the supercritical masses, and that they're storing some of the uranium as a solution for a while, which is
this is incredibly dangerous because this is more
explosive than as a solid, because the idea is when we want that neutron capture to make the chain reaction, we want a slow neutron. We don't want a fast neutron. It's like in order to be captured, you have to be moving slow enough that it can be grabbed by the atom. If it's going too fast, it's going to just bounce off and ricochet harmlessly off the atom. But the slow neutron, easier to bumps into it, it gets grabbed, it gets absorbed, you have your explosion. So in a solution, in a liquid phase, the water slows the neutrons down and thus makes it more efficient at grabbing those neutrons. So he was like, "Ooh, we should make sure to inform these people how this actually works." And the military was like, "No, no, 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 no. We want to make sure that people aren't learning too much of what they're doing." And it's like, no, in order to keep everyone safe, they need to understand everything of what's going on, or else we're going to have some really big problems. So he brought up a lot of that, and all the scientists were a little cavalier. Robert Oppenheimer up there, when he first saw the fat boy explode in Alamogordo, was said to have quoted the Bhagavad Gita, saying, "I am death, the destroyer of worlds," discussing this is the true power of the atom right here. That not long after our first test, we dropped Little Boy on Hiroshima on August 6th. On August 9th, we dropped our second Fat Man on Nagasaki. These towns were chosen specifically for, one, their military importance, their visibility due to weather, and the fact that there was limited previous damage. We wanted to see how much damage these does.
These two sites were perfect military test cases for the destructiveness of the nuclear bomb. Tokyo, for example, had already been firebombed and largely destroyed. These two were relatively untouched.
So when the first one went off, 1 pound of uranium was 13.5 thousand pounds worth of TNT, a total destruction of within a 1 mile radius of the crater. In the center of that first explosion, it was 3,000 degrees. It was said that after being dropped, the gunner of the plane that dropped the bomb said, "My God, what have we done?" It's just we've done horrible things when it comes to bombing these places, but the fact that one bomb was enough to cause this much damage was just such of a shock. I mean, we really didn't know what we're doing. We had an idea, but we were a little sloppy at times. Just for example, there's two of the Los Alamos scientists died after the fact, not directly due to the work here, but they died just because their cavalier attitude of Harry Dothlian and Louis Slotin were both
Killed in accidents in the lab due to exposure to radiation.
were one of them was just kind of playing around with the nuclear pile, working late by himself, and was like accidentally caused a plutonium core to go supercritical for a few seconds, and thus give himself a highly large dose of radiation. He stopped it, went to the hospital, and said, "I'm going to die," and proceeded to essentially try to best document the effects of radiation poisoning. Louis Slotin had a similar situation where he was showing some guys how to set things up, and would kind of like, like jury rigs on, like cut some of the corners that you're maybe not supposed to cut. And then, of course, accident happens and dosed everyone with the radiation, but him especially lethally with radiation. So, I mean, we didn't really know what we're doing for the most part. And the fact is, not long after that, we really were not sure about radiation. We were like very we had like radium painted dials on the watch. If you read anything about the radium girls, how the radium would eventually give them horrible cancers in the jaw and cause their jaws to disintegrate because they'd have to lick the brush on the to paint the watch face just to have these glow in the dark watches because they'd be dipping it into radium based paint. I mean, people were like thinking ingesting radium for their health. So we didn't really know the true effects afterwards till much later. Now, whether being used in a bomb or at a power plant, there's still some fundamental laws that must be obeyed. First is the law of conservation of mass. This law states that mass can neither be created nor destroyed as a result of a chemical transformation. And then the law of conservation of energy, which simply states that energy can neither be created nor destroyed as a result of chemical transformations. So how do we have these things where we take two masses that are seemingly the same and produce energy from seemingly nowhere? Well, in the fission process, we're going to see the formation and loss of matter and energy, because what's actually happening is matter is converted into energy and back vice versa. Einstein was the best person to put this succinctly into an equation that energy equals mass times the speed of light squared. That the mass lost times a fundamental constant squared is equal to the energy that is produced. He eventually won the Nobel Prize for this and a few other things. So what is actually the mass lost? It didn't look like there was any mass loss, but there was some mass loss. And that is the mass defect. The mass defect is simply the difference between the mass of the atom as a whole and the mass of all the individual protons, neutrons, and electrons that compose it. If we added up all the protons, neutrons, and electrons and then compare that to the actual atomic mass of the isotope, there's a small but significant difference. Now, this energy, this is responsible due to the binding energy. This energy turned into a mass, the energy that holds the nucleus together as a coherent whole. This energy equivalent of the atom's mass defect. So let's show this calculation right about now. To calculate the mass defect, we need to look at the difference between the atomic numbers of the protons, neutrons, and electrons from the actual atomic mass. So let's look and see how much energy could be generated from the hydrogen bomb. We're going to combine simply two hydrogen to one, and tritium into helium to and two neutrons. That's it, two neutrons. So looking at that, first let's figure out what is the binding energy of each guy. What is the mass defect inherent in each one? Let's just do a quick thing. Relevant. We have the mass of proton, neutron, electron, the mass of the deuterium, tritium, and helium. What is the mass defect in deuterium? So deuterium is one proton, one neutron, and one electron. Let's see. So adding them up, you get 2.0165. Now let's compare. I'll round it there. Let's see. So the difference between 2.0165 and 2.0141 is the mass defect. So the minus 2.0141 mass defect of something like 0.0024. Not a big mass defect, but that's fine. let's compare tritium. Tritium is going to be 1 proton, 2 neutrons, and 1 electron. Sum them up. You got a mass of 3.0255. We subtract out our actual mass, 3.0160. You get a mass defect of 0.0095. A little bit bigger of a mass defect, a lot more energy stored in there. If we could do the same thing for helium. Would have 2 protons. Helium, 2 protons, 1.007 times 2. 2 neutrons, 0.0009 times 2. 2 electrons, 0.0005 times 2. So you would essentially have twice that of deuterium. 0165. You get a mass of something like 4.033. Now, if you compare that to 4.0026, you get a mass defect about 0.0304. So you get a much bigger mass defect there. Now, let's go back to our original situation of how much energy could be generated in the hydrogen bomb. So remember, this is 2.0141. That's 3.0160. The other side is 4.0026 and 2 neutrons, which is 1.009 times 2. So the mass defect from side 1 to side 2, 0.009 times 2 plus 4.0026 minus 3.0160 and 2.0141. The mass defect, the total mass defect, is closer to 0.9905 AMU. If you had 1 mole of, basically, if you had 1 mole, which we haven't quite learned what a mole is, we will soon, but if we have basically 1 statistical unit of this, how much energy would this be? 1 statistical unit times the speed. I have to turn this into kilojoules. I mean, into kilograms to do the calculation. 2.998 times 10 to the 16th. If I had a mere 1 gram of deuterium when I did this, 1 gram of deuterium would produce something like 44,513,089,810 kilojoules of heat. That is a massive amount. Just 1 gram of deuterium with enough tritium to make that go that'd be a lot of heat, a lot of energy. So mass defect, a lot of energy stored in there. Now, as we look at this, we can see that if we were able to completely convert 1 gram of matter into energy, it would be enough energy to run a light bulb 100-watt light bulb for 29,000 years. 29,000 years. Turning 1 gram of matter into energy. Now, there's not a perfect conversion when we use 235. So if we use 1 kilogram, so 1,000 grams of uranium 235, the amount of energy released by that could run a light bulb 23,000 years. Not bad, but considering the fact it's 1,000. Of course, 1 gram, so 1 gram versus 1 gram, 235 could run a light bulb 23 years. Not great, but still 23 years is a long time. Compare that to efficient burning of gasoline. And when we burn 1 gram of gasoline, it is far from efficient. But if we were to burn 1 gram of gasoline and get all of the energy, you'd only be able to run that for 8 minutes. 8 minutes versus 23 years. That is a big difference. And of course, if we were to eat 1 gram of sugar, the amount of energy we'd get from sugar is slightly less than 3 minutes. So 8 minutes versus 3 minutes. Gasoline versus sugar versus uranium. The splitting the atom. 23 years versus 3 minutes, 8 minutes. So there is a huge difference. Now, fission isn't the only possibility. There's also the example of fusion. Fusion is the process by which several nuclei of small mass combine to form a single nucleus of larger mass. This is the basic concept of what happens in the sun. How does the sun produce light and energy for the entire entire solar system? It's going to be fusion. We need high temperatures, high pressures. We need something like 10 million to 100 million degrees Celsius for this to happen. But when it does, we can have things like, essentially, the net effect is 4 protons of hydrogen will undergo a series of fusions to form essentially 1 helium atom and 2 beta particles and 2 positrons, which then will collide and form 2 gammas. Of course, there's going to be a lot of different steps where hydrogen fuses together to form deuterium and something else, and like a beta particle, and then deuterium fuses together to form tritium, and they form some like helium-3, but eventually it goes to helium. Now, we actually can create a fusion bomb where it's called our H-bomb. 9 years, we eventually found something even more powerful than uranium. The idea is that a fusion bomb works by, we take deuterium, which is naturally occurring isotope, that, remember, not very common, but it's possible to get it out of seawater, and tritium, which trace, if any. But when we hit them together with enough heat, they will fuse and to form helium and a neutron and a whole heck of a lot of energy. Now, the trick of this is you need small amount of fission to initiate this. You need essentially an atom bomb to initiate the hydrogen bomb, because the deuterium can be concentrated, but because we need the high heat and high pressure to make this go. We can concentrate the deuterium, but we also have to generate the tritium on site. And we generate the tritium by bombarding lithium with neutrons, which will form tritium and an alpha particle as the byproduct. But so we're capable of generating this, and it's even far more energy than our A-bomb, and far cleaner. Now, of course, at this point in 1963, we wrote several treaties that prohibits testing of nuclear of these bombs either in space, underwater, or on ground level. Now, we haven't banned the testing underground, but we're trying to do this to prevent any radiation, especially any fallout. Fallout is simply the fine radioactive debris that is released into the atmosphere by nuclear explosion and accidents that settle to the earth. While most uranium fallout, it it's quick to dissipate. They said that Hiroshima was like safe to walk within, I think, a couple days. But there's actually some radioactive material that is far more dangerous, some like cobalt 60. That cobalt 60 is the type they'd use in a dirty bomb.
which is the equivalent of simply salting the earth.
The idea is that the fallout is so long lasting that it's going to take several, like a generation, before the place isn't radioactive anymore. That it produces radiation that can't be outweighed. Like, it's going to be so radioactive that, I mean, it's a slow radiation. It's going to, instead of building up and go all at once, it goes year by year by year. It's just slowly leaking more radiation into the environment, thus killing all the plants and causing mutations and killing all the people. It's just a dangerous radiation that kind of ruins the area for everyone involved. So now that I've thoroughly impressed everyone, time for our little thought experiment. Was it a good idea that America specifically got the bomb first and got it when it did? There are so many books and movies and TV shows all about alternative universes where someone else got the bomb or someone else used the bomb. It's great. It's not very great for the Japanese, but it's great for the world that we got the bomb and it's only been used twice. It hasn't really been used since then, at least militarily. That, think about it. We have books like uh, The Fourth K by Mario Puzo. We have things like A Canticle for Leibowitz. We have many Robert Heinlein novels that talk about what happens if China was to essentially nuke America. We have shows like Man in the High Castle, or what if the Nazis got the bomb first and nuked DC. We have many different classic episodes of The Twilight Zone of what happens when we have mutually assured destruction. What about movies like Doctor Strangelove, talking about like, well, oops, we accidentally bombed Russia and they have an automated defense system that's going to bomb us back. Most of the Cold War of what happens if we essentially have a nuclear holocaust. I mean, even Weird Al wrote a song, Christmas at Ground Zero. What's going to happen? There's many game series like Fallout discusses this theory. What happens? Is it good that we got it when we did? Is it good that we got it first? I mean, just for example, would it have been better if we'd gotten it earlier or later? If we got it earlier, maybe we'd have nuked places like Iwo Jima instead of mainland Japan. But maybe we would have used more nukes on them. Maybe we would have nuked Tokyo as well instead of just firebombing Tokyo. Maybe if we got the bomb much later and during a different war, we would have nuked like the Middle East, not knowing how much damage it could do. Maybe we would have had worse technology. So think about, would have been better. The science would have been more advanced. We might have had more devastating options. Maybe we would have nuked all of Russia. Who knows? Because we were think about it from the perspective that the war was winding down. We needed that little bit of thing to kind of push Japan over the edge. We only really had material for 2, 3 nukes, and so we used them. Yeah, we built more later, but the fact of the matter is we used just about all of our material on that campaign. Would have been better to wait for that till we had more material. Who knows what would have happened? So to think about that. So have a good day. I will speak to you about chapter 5, where we'll go into some of the nicer aspects of the nucleus and not all gloom and doom and death and destruction. Goodbye.